All right, so in this set of notes, we're going to start looking at our different types of recurrence relations and seeing if we can find patterns for their general rules. So the first one, if we think about a first degree linear homogeneous recurrence relation, that means that our relation is going to take the form u sub n equals a times u sub n minus 1. Well, if we think about that, that's the same as a times u sub n minus 2. Because u sub n minus 1 is going to be a times u sub n minus 2, and so on. This is just a geometric sequence. And we know the general term for a geometric sequence is a to the n minus 1 times u sub 1. We could rewrite this, getting rid of the n minus 1, and just have a sub n times a to the negative 1 times u to the 1. Well, those are both constants, so I could have some k value as my constant. So there's our first sort of general rule, the easiest one. Now if I want to look at non-homogeneous recurrence relations, well, here's my general formula with the recurrence relation. Let's try to get it into a general formula using just n. So I'm going to do the same thing. I'm going to rewrite my u sub n minus 1. So let's write that down. U sub n minus 1 is going to be a times u sub n minus 2 plus f of n minus 1. So then if I plug that in, u sub n equals a times u sub n minus 2 plus f of n minus 1 plus f of n. I could expand that. A squared times u sub n minus 2 plus a times f of n minus 1 plus f of n. I could do the same thing, u sub n minus 2. I know that's going to be equal to a times u sub n minus 3 plus f of n minus 2. Substituting it again, I could say un is a squared times a un minus 3 plus f of n minus 2 plus a f of n minus 1 plus f of n. And this is allowing me to see a pattern here. So I've got a cubed un minus 3. Again, that's my geometric sequence, plus a squared f of n minus 2, a f of n minus 1, plus f of n. So it looks like I'm going to have my geometric sequence here. So that's going to be a to the n minus 1 times u1. And then I've got a sequence here that I can turn into a series. So I'm going to start with, let's go with some value k equals 0. And then I'm going to go up to n minus 2. I'm going to have a to the k times f to the n minus k. Okay, so notice I would start with k equals 0, so I'd have a to the 0 times f to the n. That matches up. Keep going all the way until I have my n minus 2 in there, and that's going to give me what I need. Okay, so this one we know, and we could rewrite it as we did up here with some other sort of constant. This one, however, is more difficult, and I can only figure this out if it's something that we know. So it's all going to depend on what the function is. If the function is a geometric sequence or an arithmetic sequence, then we would be able to find a general term for it. So, for example, if my f sub f of n was just a constant, so if f of n is some constant c, then we would end up with a to the n minus 1 times u1 plus c times the sum of k equals 0, n minus 2 of a to the k. Well, this is just a geometric series. I know the formula for that. Okay, so I'm going to separate this out a bit because this was my general term. And now this is a special case for if my function is actually just a constant. So I know my formula. My formula, this part stays the same. And now my first term is going to be 1 times a, that's my common ratio. The number of terms is n minus 1 terms because I'm starting at 0, minus 1 over a minus 1. Well, I can rearrange this to factor out my a to the n minus 1s, and I could then rearrange it as I did above to be a constant. So I'm going to end up with some constant times a to the n plus some other constant. So my other constant is going to end up being the c times negative 1 over a minus 1. And of course, all of that's going to depend on my initial conditions, which I could solve for. So generally, first degree recurrence relations have this form. Specifically, if my function is just a constant, I would end up with this form. But again, we can always just list terms to help us see what's happening to try to get the general term as well. So we're going to look at some examples of that coming up.